Good morning, distinguished guests, participants, and fellow academics from across Asia. It is an honor to be here today at the 10th Asian Young Geotechnical Engineers Conference and the 28th Annual International Conference on Geotechnical Engineering in Jakarta from November 11 to 13, 2024. We extend our warmest welcome to all of you. Today, we will present our paper titled, Rigid Inclusion Numerical Simulation on Strengthening the IKN VVIP Airport. Next. Our outline. Introduction. Method. Result. Discussion. Conclusion. Next. First introduction. The construction of the IKN VVIP Airport, in alignment with Presidential Regulation No. 31 of 2023, is a pivotal project aimed at enhancing connectivity to IKN, catering to the needs of state leaders with reduced travel time and distance. This research delves into the technical planning and operational aspects of the airport, with a special focus on the challenges posed by the site's soil conditions and the innovative soil improvement methods employed to address these challenges. The soil investigation at the IKN VVIP airport site revealed the presence of soft soils, problematic stones, or clays, and expansive, organic, and peaty soils, posing significant construction challenges. To meet the airport's operational timeline, a combination of soil improvement methods, including rigid inclusion, prefabricated vertical drain, prefabricated horizontal drain, and deep soil mixing, was employed. The research utilized the finite element method numerical analysis software LISA V.8 to model the behavior of the settlement and stress in the existing soil, providing valuable insights into the effectiveness of foundation reinforcement with the rigid inclusion method. Next. Methods. Soil investigation and site characterization. To evaluate geotechnical conditions, a soil study was carried out, which included sample collection and laboratory testing to identify the kind of soil, bearing capacity, and settlement potential. The findings showed that the development of airport runways would be complicated by soft soils, difficult clays, and organic, expansive, and peaty soils. On the airside of VVIP IKN Airport, 3 primary soil strata were found. Upper layer, compressible clay, 1.0 to 11.5 m thick, with NSPT values less than 10. Middle layer, NSPT values 11 to 30, thickness 1.0 to 9.5 m, stiff clay with some sand intercalations. Lower layer, claystone, which may weather quickly, with NSPT values exceeding 60, possibly clay shale. Additional qualities will be verified in laboratory reports. Next. Rigid inclusion is a soil improvement method. For constructions with consistent loads and substantial allowable settlement, rigid inclusion techniques increase soil bearing capacity and decrease settlement. In order to balance cost and dependability, rigid inclusion designs in Indonesia usually incorporate a safety factor of at least 1.5 for axial bearing capacity. Confirming real-world capacity requires load testing, especially close to embankment edges where rigid inclusions are subject to moment and tensile forces that could result in differential settlement and landslide hazards. To keep these columns stable in the face of tremendous stresses, reinforcement bars are inserted. This technique is applied for repairing Category A1 infrastructure, such as Zone 2 taxiways and airport runways, where a low tolerance for settlement is necessary. Next. Modeling and simulation. Afterwards, the soil investigation, LISA V.8, was used to develop a comprehensive runway model that included the runway structure, rigid inclusion reinforcement, and soil conditions. This model used finite element analysis to simulate static, dynamic, and seismic loads, offering insights into the distribution of stress and settlement. Accurately modeling soil structure interactions was made possible by LISA V.8's capacity to handle complicated geometries and materials. With the help of the software's multi-threaded solver, integrated modeler, and graphical post-processor, big projects like the IKN VVIP airport may be analyzed effectively. It supports a variety of element types and boundary conditions and is especially well suited for managing high computational demands in projects with intricate soil conditions. Next. Result. Rigid inclusion axial bearing capacity. Although it has a direct impact on when pavement work begins, finishing the rigorous inclusion work is essential to maintaining the IKN VVIP airport project's timeline. Since materials are scarce, a 35 cm thick reinforced concrete slab similar to the Beijing-Tianjin high-speed rail project is utilized in place of LTP. The axial bearing capacity of rigid inclusions for Zone 2's runway, as determined by NSPT data at dB22, is 646 knots at a depth of 14 meters. A live load, concrete slab, and embankment are among the combined pavement loads that add up to 140 knots per square meter. The stiff inclusions support 405 knots each and have a safety factor of 1.59. They are arranged in a 1.7 meter square configuration. The placement of reinforcement bars D13-100 and D10-100. Next. The 3D modeling simulates load conditions. Positions in the rigid inclusion layout are 1,700 mm apart in both horizontal and vertical directions, following a grid pattern. To increase stability, two reinforcing bars, D13-100 and D10-100, cross in a cross pattern. Based on Figure 8, the first 3D model takes into account a surface load of 140 knots per square meter, yielding a settlement value of 0.00061 m. At a depth of 14 meters, the stiff inclusions are anchored in clay with an NSPT of 60. From 0 to 14 meters, no soil friction resistance is assumed, allowing for unrestricted movement. Next. In the initial condition, 3D modeling is carried out according to Figure 8XX with the load given on the surface of the concrete slab is 140 knots/m2. From these results it is obtained that the settlement value that occurs is 0.00061 m or 0.616.1 mm with the condition of the tip of the pole assuming rigid anchorage with clay hard soil conditions with an NSPT value of 60 at a depth of 14 m. At a depth of 0 to before 14 m it is assumed that there is no soil friction resistance, so it is assumed to be free to move. The given picture shows a finite element analysis showing the distribution of von Mises stress in a structural element made up of several columns. The von Mises stress fluctuates throughout the structure and is a crucial measure in forecasting the yielding of materials under complex loading situations. Stress values range from 67.04 knots per cubic meter to 866.9 knots per square meter, as indicated by the color-coded legend. The upper third section of the columns, indicated in red and orange, has the maximum stress concentration of 866.9 knots per square meter. This suggests possible risk sites that, if ignored, could result in material failure because these areas are exposed to heavy loads. Next. Discussion. In the next condition, 3D modeling is carried out according to Figure 9 with the load given on the surface of the concrete slab is 140 knots/m2. From these results the value of the settlement that occurs is 0.00057 m or 0.575.7 mm with the condition of the tip of the pole assuming rigid anchorage with clay hard soil conditions with an NSPT value of 60 at a depth of 14 m. At a depth of 0 to before 14 m it is assumed that there is soil friction resistance, so it is assumed that the pole does not move towards the x-axis, or displacement equals 0 in the x-axis. And in the y and z-axis there is still movement. Presents a finite element analysis of a structural component's von Mises stress distribution. The color legend indicates stress values from 67.73 knots per square meter to 800.9 knots per square meter. The maximum stress, 800.9 knots per square meter, occurs within the upper third of the columns, marked in red and orange, signifying areas of high load concentration and potential yielding risk. This high stress concentration highlights critical zones requiring reinforcement or design modifications to prevent structural failure. Next. In the next condition, 3D modeling is carried out according to figure 141 with the load given on the surface of the concrete slab is 140 knots/m2. From these results it is obtained that the settlement value that occurs is 0.000534 m or 0.535.3 mm with the condition of the tip of the pole assuming rigid anchorage with clay-hard soil conditions with an NSPT value of 60 at a depth of 14 m. At a depth of 0 to before 14 m it is assumed that there is soil friction resistance, so it is assumed that the pole does not move towards the x and y axis, or displacement equals 0 in the x and y axis. And in the z axis there is still movement. Shown in the figure 15102, a finite element analysis of the von Mises stress distribution of a structural component. Stress values range from 68.08 knots per square meter to 751.1 knots per square meter, as shown by the Kohler legend. The upper third of the columns, which is highlighted in orange and red, contains the maximum stress of 751.1 knots per square meter, indicating areas of high load concentration and possible yielding danger. This significant concentration of stress points to crucial areas that need to be reinforced or have their design changed to avoid structural failure. Next. Conclusion. Finite element analyses of structural columns reveal a maximum von Mises stress of 866.9 knots per square meter, predominantly in the upper sections of the columns. These stress levels fall well below the allowable stress limits set by the Indonesian national standards for concrete strengths of 20 MPa and 35 MPa, which permit 12,000 knots per square meter and 21,000 knots per square meter, respectively. For the lower concrete strength, cracking stress is limited to 6,600 knots per square meter, while for the higher strength, it's capped at 11,550 knots per square meter. This margin confirms the structural integrity and resilience of the design under operational loads. Initial displacement analysis under a 140 knots per square meter surface load on a concrete slab indicates a displacement of 0.61 mm. The setup assumes rigid anchorage within firm clay soil conditions at a depth of 14 m, allowing free movement in the absence of soil friction resistance up to that depth. These conditions affect the overall structural behavior, especially in load distribution. Subsequent finite element analyses illustrate stress distributions with von Mises stress ranging from 67.04 knots per square meter to a peak of 866.9 knots per square meter, concentrating primarily in the upper third of the columns, where the risk of material failure under heavy loads could be higher. These insights enable engineers to optimize structural design, reinforce critical stress areas, and ensure durability by addressing load distribution and material strength effectively. In conclusion, we hope that our research has offered valuable insights into the role of rigid inclusions in strengthening critical infrastructure like airport runways, especially in areas of strategic national importance such as the IKN VVIP airport. We believe that continued innovation and collaboration in geotechnical engineering will be essential in addressing the complex challenges of modern infrastructure development. Thank you for your time, attention, and the opportunity to share our findings. We look forward to your questions, feedback, and a productive discussion. Thank you once again.